Go.
Hello, our names are Danny and Morgan, and we are presenting about the engineering issues given to us when you're trying to determine the composition of both the crust and mantle.
The composition of the crust and the mantle are hard to determine because of multiple factors. Unlike surface geology, they cannot be directly observed and samples cannot be taken. Also, the thickness of these layers prevents many geophysical methods from being able to penetrate and categorize the rock. Large amounts of energy are needed to reach the depth of the mantle and beyond. The human instruments rarely can reach this level of power. However, natural sources such as earthquakes can reach this depth and reflect back to the surface. For this reason, seismology is one of the main methods along with electromagnetic methods.
Seismology is useful as waves are able to propagate far into the earth. They will reflect, refract, and change speeds at discontinuities. Therefore, seismology is useful for determining different rock properties and their locations. There are many types of seismology. However, for this problem, there are specific types or wavelengths that work best. One type of seismology used for this problem is long period. The long period receivers for this type of seismology collect waves between the frequencies of 0.05 and 0.01 Hertz. They are therefore useful for constraining average lithospheric properties. The long period waves are sensitive to changes in shear velocity and will show structure well. However, this method is weaker when conducting more regional studies. Another type of seismology used is deep sounding refraction, or DSP. These generally use explosions such as bombs or nuclear weapons for their source of energy, and sometimes will use earthquakes. They record frequencies from 1 Hertz to 50 Hertz. In recent years, the large number and more dense receivers have been able to capture the mantle in more detail. The next type is known as broadband. It is newer and able to collect waves ranging from 0.01 Hertz to 50 Hertz. This allows the receiver to record more waves and permits the analysis of a variety of seismic phases. This type rests between the other two types of studies mentioned. The figure to the right-hand side of the screen shows different ray paths in seismic surveys, where the stars are sources and the triangles are receivers.
Electromagnetics was used to study the mantle in the 1970s. However, moved to the focus of the crust after improvements to instruments were made, processing for higher frequencies easier, and more focus for the interest of the age, i.e., research was focusing on understanding the crust, so instruments were improved for that purpose. The propagation of EM waves relies on the conduction of currents. There are two types of current conduction, electronic conduction and ionic conduction. The electronic conduction is the dominant conduction mechanism for most solid materials and is therefore governed by absolute temperatures of the material and other parameters. The ionic conduction is the dominant conduction mechanism in fluids, but is also important for olivine at high temperatures of 1100 to 1200 degrees Celsius. That being said, the melting temperatures of olivine is 1900 degrees Celsius, which is a large percentage of the mantle composition. In recent years, EM has once again focused on understanding the mineralogy of the mantle. The premise of using EM waves to understand the mantle is dependent on the induction of a telluric field in the earth, which is dependent on the conductivity of the medium. That being said, given the magnetic and electric fields and determining their ratios at varying frequencies, you can establish a model of conductivity variation for depth and distance, i.e., the change in composition. The table to the right shows a study by Alan G. Jones, who used electromagnetic methods to image the continental upper mantle. This table shows the range of resistivities from the upper crust to the upper mantle. These resistivities can also be interpreted as the opposite of conductivity, meaning that because the upper crust is more resistive than the lower crust, The lower crust is more conductive than the upper crust.
The surface geology of the crust gives us many insights to what the composition of lower areas of the Earth could be. Rock properties recorded on the surface can be compared to the properties recorded by geophysical methods. There are many types of rock that can be recorded on the surface that can be seen at depth. One good example of this is kimberlites, which are believed to be composed of the same material as the mantle. They are geologic structures that formed from eruptions and are very rare. They contain at least 35% olivine and sometimes diamonds, both of which are not normally found or formed in crustal layers. Using the properties of the rock, like density and shear modulus, we can understand how they would appear to geophysical instruments and models. The figure on this slide shows kimberlites on the surface of the Earth. South Africa's wealth from diamonds and minerals can clearly be seen and is attributed to the existence of these structures. Even Colorado has a small deposit of diamonds from these structures.
The Earth's crust can be identified as the portion that floats on top of the mantle. This is due to the less dense material that the crust is composed of. The Earth's crust can be split into two categories, the continental crust and the oceanic crust. The average thickness for the continental crust is 35 to 40 kilometers. This is composed of an andesitic bulk composition. The continental crust can also be split into three categories based on assumed compositions from different case studies. The upper continental crust mineralogy is identified as 60% intermediate, meaning mostly composed of silica rocks. These include quartz, feldspar, and others. The middle continental crust is composed of 69% silica rocks and 16% conundrum. Lastly, the lower continental crust is much more mafic and is composed of 50% silica rocks, 15% corundum, and about 10% of each comatite and carbonatite. The image to the right shows a diagram we constructed that shows the relative distribution of volume per location in the Earth's center. This image also shows the location of different discontinuities between the different boundaries. This is not drawn to scale.
The oceanic crust is more dense than continental crust. This section of the crust mainly consists of a homogeneous basalt, which contains plagioclase, pyroxene, and occasionally olivine. Its average thickness is around 6 to 7 kilometers and is significantly younger than continental crust. This crust is constantly being generated at mid-ocean ridges. Here, magma cools in different phases. Some comes into contact with cold seawater, leading to rapid cooling and a finer structure. Cooling of the magma is slower the deeper it is, leading to more coarse-grained structure. The crust recycles itself at subduction zones, diving into the mantle, as they sink beneath the continental crust that they are coming into contact with. The mantle is located between the Moho discontinuity and the Rigidi discontinuity, and can be separated into the upper and lower mantle. There are three distinct differences between the upper and lower mantle: location, temperature, and pressure. The upper mantle is the layer between or beneath Earth's crust, and it's also known as the bottom of the lithosphere. This portion of the mantle lies 403 to 660 kilometers in depth. It is mostly composed of solid silicates. The lower mantle is located beneath the upper mantle at a depth of 660 to 2,900 kilometers. The temperature of the upper mantle is 500 to 900 degrees Celsius, while the average temperature of the lower mantle is much hotter at 7,230 to 400,000 degrees Celsius. The pressure of the lower mantle is much greater than that of the upper mantle, which helps increase the viscosity of the lower mantle. However, the upper mantle is still more viscous than the lower mantle.
Seismic and electromagnetic surveys provide useful information about the composition of the mantle and crust. However, equipment and techniques are continuing to improve. That being said, all of the surveys have their own flaws and are still not able to provide significant information about the underlying geology. Each case study we reviewed, we were able to use as a reference to the differing perspectives and findings on the assumed underlying geology. For instance, surface geology provided a good starting point for geologists and geophysicists to form their assumptions. However, instruments are not accurate enough to provide exact percentages of the composition of the crust and mantle or a detailed map of the layers of the rock deep beneath the earth. That being said, there is a fair amount of research to assume that the crust is composed of 60% silica rocks and the mantle is composed of about 40% oxygen, 20% silicone, and 20% magnesium. Geophysical survey methods are constantly becoming more accurate and reliable. The tools available are higher quality and can transmit and record more information. For seismic, the instruments are able to record waves with a wider frequency, such as broadband surveys. This technology will likely be applied to other settings in the future. The composition of the crust and mantle of Mars is another geophysical problem with many of the same attributes. By improving the knowledge of our own planet's crust, we are able to understand how to survey and map exoplanets in the future.
Thank you for listening.